In this segment, we will talk about CPU scheduling and all the different policies. First, we'll talk about why we need CPU scheduling, um, why we need to multiplex different tasks on the CPU, and how we're going to do so. And then we'll talk about the different policies that are possible. The first reason why we need CPU scheduling is because a typical process does not just need the CPU. It needs other parts of the system as well. For example, I/O. Let's say you print on the disk. You write things to the disk, or you want to print things on the screen, and a few other possible forms of I/O. And in general, I/O systems are much slower than CPU. So typically, an I/O response time is something like 10 milliseconds. So it takes about 10 milliseconds for the disk to write a byte. And if you look at your CPU, it can possibly do an instruction every nanosecond. So there's a big difference between the I/O and the CPU. So what's going to happen is that typically a process would first do some CPU work, and then it's going to do an I/O burst. And when it has an I/O burst, essentially it cannot do anything else. It's got to wait for the I/O to complete. And then it's going to come, the I/O is going to finish, you get back to your CPU burst, and then there's going to be another I/O burst, and again, your CPU is not used during this time period. So during the periods of I/O burst, your CPU utilization drops to 0. And during periods of CPU burst, your CPU utilization is 100. So the primary goal for CPU scheduling is to make use of the CPU during these I/O burst periods, when this specific process is off doing something else. You want another process to take advantage of the CPU in the meantime. So if you look at essentially how I/O bound, there are lots of I/O bound versus CPU bound. There are lots of different possibilities for different processes. So on the top, I've shown you a long CPU burst where the long periods of CPU burst interleaved with I/O bursts, and then at the bottom, I've shown you short CPU burst interleaved with I/O bursts. Obviously, these two systems require very different scheduling characteristics. The long one, you got to make sure that the scheduler overheads are not high, and most of the time is spent by the application of the CPU. And with the short one, you got to make sure that because you kick in every so often, the scheduler kicks in more often than in the long burst system, that its overheads are not overriding. In this segment, I will use the term process and threads interchangeably sometimes. When I use the term process, I only refer to a single thread process, so I'm only scheduling one thread at a time. The scheduling job can be applied to both threads or processes. And the term job is referred to as a CPU burst or a compute-only process, right? So when we talk about the different scheduling algorithms, the term job refers to a process that has only a CPU burst, so no I/O bursts. With CPU scheduling in general, you have multiple queues. You have an I/O request queue. Um, you have a few other ones. For example, if you fork a child, you interrupt wait queues, and all of these queues have different processes waiting on them, right? So here's your ready queue. Here's all the processes that are ready for the CPU, and so then the scheduler can pick one of them. And then you've got these other queues, such as a time slice, those which have the time slice expired, those which have forked a child, those are waiting on an interrupt. All of these ones hold processes that are not yet ready, but at some point they will become. When they become ready, then they go back into the ready queue, and when that happens, then the scheduler can kick in at that point and pick one of the processes from the ready queue to start running on the CPU. Another notion that's important is the notion of preemption versus non-preemptive scheduling. Preemptive means to forcefully stop something and then do something else. So with preemptive scheduling, the OS can forcibly remove a process. With non-preemptive scheduling, once the CPU has been allocated to a process, unless and otherwise the process itself yields in some fashion by either making a system call or by completing or have some form of I/O, then the OS cannot. Only then can the OS pick another process to run. With preemptive scheduling, the OS can periodically, based on some parameters, kick in, take out the process currently running on the CPU, and then put in another one that does. There are lots of different scheduling criteria. Some of the ones that we can explore are CPU utilization, which is the percentage of time when the CPU is busy. If the goal is to make sure your CPU is busy, then you want to make sure that your applications run as long as possible. The CPU and the scheduler, which is technically overhead, does not occupy a large fraction of the CPU's time. CPU utilization is essentially the fraction of the time spent by the CPU in doing useful work. This is not only dependent on the scheduler itself, but it's also dependent on the application. If you have applications that are going to do a lot of I/O tasks, then it's highly unlikely that you're going to achieve high CPU utilization. Then there's the throughput argument. This is your cloud computing argument, where you want to run as many processes as possible and complete them in the shortest time possible. So you want to complete all the tasks in the shortest time. Then you have response time, which is like a web server, which is the amount of time to finish a particular process. So you want to make sure that you satisfy every web request of yours within 99th percentile of a certain response time. Right? So you want to satisfy 99% of the requests that come into your web server in a certain amount of time. So in this case, or if you have things like Google Docs, interactive priorities, extremely important. Finally, there's waiting time, which is the amount of time the process waits in the ready queue before it starts execution. This is very important for interactive processes to make sure that you're not waiting for a long time, even if you maximize throughput, right? So if you essentially have to make sure that all tasks are responsive and that they're getting the appropriate time to do the things, the display or the I/O. For example, if you hit a keystroke, it can't take a long time for it to appear on the screen, right? There are lots of different goals. Obviously, as we spoke about, you can maximize utilization or throughput or even response time. And typically, these goals cannot be achieved simultaneously. And so each of the specific algorithms you look at will try to optimize one or more of these metrics, but may possibly sacrifice some of these other metrics. And they sacrifice it based on the system conditions, right? Based on what the average latency of each of these tasks or jobs that come in are, based on what order they come in. There are lots of different system parameters, dynamic system characteristics that influence each of these parameters. So we're going to look at quite a few of the scheduling algorithms. We're going to look at first come, first served, round robin, shortest job first, priority based ones, and then finally lottery scheduling. We'll look at each of these in order, and we'll look at the pros and cons for each of these algorithms.